So today we're going to look at module 4, which is Laplace transforms. So in this module, we're going to cover 3 different sections. So we're going to look how to apply partial fractions in differential equations. And then we're going to look on how to solve differential equations using Laplace transforms. And finally, we're going to look at the application of Laplace transforms to circuit analysis. So first, we start with partial fractions. Okay, so you can read the definition of partial fractions and in these tables, all right? So you can see that on your left-hand side, you have a denominator, and your right-hand side is the decompositions based on what denominator you have on your left-hand side, all right? So we will look in examples on how to apply these tables when we want to apply partial fractions. So we jump to example 1. So we're going to solve these problems using partial fractions. And we also have initial values informations where we will use to find our constants value C. So we have dx over dt equal to negative x squared plus x. So we can also write this to becomes negative x minus 1. So we put x with dx and t with dt. So we have 1 over x minus 1 with dx on the left-hand side, and we have dt, negative dt on the right-hand side. After that, we apply integration on both sides. Okay, so on the right-hand side, okay, we can direct solve. So we become negative t plus c. But on the left-hand side, okay, so this is on the left-hand side. To solve left-hand side, we apply Laplace transforms. Okay, so we apply Laplace transforms. So we have 1 over x minus 1. So the denominator, okay, we can write these expressions in terms of decompositions, okay, where the denominator is being decomposed into 2 different parts, which is the first part is x, and the second part is x minus 1. Okay, so if we refer to the tables, so the left-hand side is our denominator. So if we have x only in our denominator, so the decompositions will becomes a. Okay, it's only a single coefficient. So we go back here, so we have a. And the second terms, we have x minus 1. So the highest power of our denominator is 1. So the coefficient will be consist only a single coefficient, which is b, since we already use a. Okay, so what it means, we can decompose the left-hand side to the one that you see on the right-hand side. So if we solve the ones on the right-hand side, it will be equal to a x minus 1 plus bx, which is equal to 1. Okay, so we can ignore the denominator term because we already make it equals. So we solve this x minus a plus bx equal to 1. So we have ax plus bx minus a equal to 1. So we have a plus b x minus a equal to 1. Okay, so we have 2 equations there. We can say a plus b equal to 0, a plus b equal to 0, And that's our first equation, and our second equation is negative a equal to 1. That's our second equation. So if we solve equations 1 and 2, okay, so we get a equal to negative 1 and b equal to 1. And we put back these equations inside our decompositions, okay? So that one will give us 1 over x minus 1 equal to a, which is negative 1 divided by x plus 1 x minus 1. Then we take integrations, okay? So instead of solving the one on the left-hand side, now we will integrate on the left-hand side. So that one will give us negative ln x plus ln x minus 1. Okay, so we can put back this inside our previous problems. Okay, so we have negative ln x plus ln x minus 1 equal to negative t plus c. Okay, so these ones we can write as ln x minus 1 divide x, okay, because this is minus, equal to negative t plus c. And to get rid of the lns, we take exponents. So we have x minus 1 over x equal to exponent negative t multiplied with exponent c. Okay, so that ones we can say this exponent c we can say is equal to exponents. Okay, so what is the value? It's equal to constant. So what is the value of constants? We apply the initial value information, where if t equal to 0, we have x equal to 2. Okay, so that ones we put back inside our equation. If x equal to 2 minus 1, 2, and t equal to 0, multiply c. Okay, so we have half will be equals to exponent 0, you got 1 equal to c. Okay, so your c will be equal to half. Therefore, we have x minus 1 divide x equal to half, okay, exponents negative t. So if you write in terms of x, okay, if you write in terms of x, x will be equal to 1 over 1 minus half exponent t. Okay, so that is your solutions. So in the previous sections, we learned how to apply Laplace transforms. And if you want to apply Laplace transforms, you need to remember how to read these tables, all right? And we go to the Laplace transforms, okay? So you can read the definitions, but the idea of Laplace transforms is to transform from time domain to S domains or to frequency domains, okay? So the application is many. You can find it especially in science and engineering. Okay, so the Laplace transforms is mathematically defined by these equations. Okay, so we can apply these equations to transform function from T domain to S domains. Okay, we look at example 1. Find the Laplace transform of ft equal to 1. Okay, but before we apply these ones, I want to bring your attention to our Laplace tables. Okay, so inside these Laplace tables, we have time domains on the left-hand side, and then frequency domain or S domains on the right-hand side. Okay, so what it tells you then, if you have ft on the left-hand side, you can apply Laplace transforms. Okay, you can apply Laplace transforms, and if you apply Laplace transforms, uh, it will transform into become capital Fs. Okay, so if you have AFT in the time domain and apply the Laplace transforms, it will becomes A with capital Fs. All right, so this will in the representations in frequency domains. So you can see the rest of the functions in these tables. Okay, so we look at example 1. So based on definitions, we have integrations from 0 to infinity, exponents to the power of negative st, ft dt. So with our ft equal to 1. So we can write this further to become exponents negative st 1 dt. So if we integrate exponents to the power of negative st, so we will get exponents negative st 1 over s negative. And then so we put back 0, the limit 0 to infinity. Okay, so you put 0 and you put infinity inside this bracket, it will be equal to negative 1 over s exponent negative s infinity. Okay, so minus negative 1 over s exponent negative s 0. Okay, so what do you get when you have exponents approaching to negative infinity, a very large number? You will get something which is approaching to a very small number. So these all things, okay, this whole thing will be approaching to 0 because exponent negative infinity will be approaching to a very small number. So if we have a very small number multiplied with 1 over s, we can assume it's approaching to a very small number as well. Okay, so it's minus with, if you have exponents, exponent 0, okay, so if you have exponent 0, you will get 1, so this whole thing will become as negative 1 over s. So finally, you will have 1 over s. Okay, so you can see that in time domains, you have that values. And in s domains, you have that values. This is the values after transformation, which is in s domain. Okay, so it tells you if you apply Laplace transforms 1, okay, on the time domains, it will becomes 1 over s in the s domains. Okay, so if you refer to your Laplace tables, okay, so you can find this information in the Laplace tables. Okay, so you can try to find it in the Laplace tables. So the second examples, we look at the transformations of exponents at t. Okay, so again, we start with the mathematical expressions where we have integrations from 0 to infinity of exponents to the power f st ft dt. Okay, so this is the mathematical definitions where our ft will be exponent at t. So we're going to apply Laplace transform to these values, and we will see what is the values in the S domains. So we have 0 to infinity exponent negative st multiply exponent at dt. Okay, so that part we can further write 0 infinity exponent, so we can combine negative s plus a t dt. Okay, so that ones will be equal to 0 infinity. Okay. So we can also write as a minus s d dt. Okay, then we integrate these whole things. Okay, so if you integrate that things, okay, so you will get itself back exponents a minus s t, and then you will get 1 over a minus s. And don't forget your limits, which is from 0 to infinity. Okay, so you put your values 0 and infinity. Okay, so this is scalar, so you can bring the scalar outside. So you can you only replace inside the brackets. Okay, for the limits. So we have 1 over a minus s. Okay, so exponents a minus s infinity minus exponents a minus s 0. Okay, so what do you get here? Okay, so if you have infinity, we'll be approaching to 0, isn't it? And if you have 0, so these things, exponents, will be approaching to 1. Okay, so you have negative 1s over a minus s. Okay, so you can also write as 1 s minus a. Okay, so you can refer these values. Okay, you can refer these values if you apply Laplace transforms. If you apply Laplace transforms of exponent at t, it will be equal to 1 over s minus a, which is, this is the time domain, and the other one is the s domain or the frequency domain. Okay, so we look at example 3. Find the Laplace transforms of ft equal to f prime t. Okay, so we start with the mathematical definitions. We have integration 0 to infinity exponents negative st ft dt. So that one will be equal to 0 infinity exponent negative st. So our ft is f prime t dt. So you can see there's two expressions of t. We have that first and that second. So to solve this, we need to use, so we solve using integrations by parts. Okay, so the equation is given as integration u dv equal to uv minus integration v du. So let's say we take u equal to exponents negative st. So our du over dt will be equal to negative s exponents negative st. So our du will be negative s exponents negative st dt. Okay, so that is our du. And we take dv, okay, we take dv will be equal to f prime t dt. So if we want to get v from dv, we integrate both sides. Okay, so if we integrate both sides, the right hand side from f prime t, it become f t. Okay, so you got all the informations, you put it back into the equations, so you will get integration 0 infinity exponent negative s t f t dt is equal, f prime t dt is equals, okay, so we have u exponents negative st multiply with v f t minus integration from 0 to infinity, we have v, which is ft, multiply du, which is negative s exponent negative st dt. Okay, so when we solve this, we will able to find our answers. But don't forget, we have a limit here, okay, from 0 to infinity. Okay, so if you put a limit, okay, so we start with that one first. If you put in infinity, okay, you put infinity inside t, okay, so if you replace t with infinity, so we have this whole components will be approaching to 0, okay, because exponents to the power of negative infinity will become very small, approaching to zeros. And if you put 0 inside t, okay, so we have minus, we put 0 inside t, so exponent to the power of negative t will be approaching to 1, okay, so 1 will be multiplied with f0. Okay, so we have minus, and s we can treat as a constant, okay, so we bring negative s outside the integration, so it become plus s integration 0 at, so we have exponents negative st ft dt. All right, so if you look at that part, anyone know what is that part? Okay, so if you look at that part, this whole thing is actually referred to the definition, isn't it? So which is, we can say that the Laplace transforms of ft, okay? So we can also write this part as we have equal to 0 minus f0 plus s, okay? So this whole thing is go back to your definitions. So it's the same as if we apply Laplace transforms to our definition f, or to our function ft. Okay, to our function ft. So you can write back as s ft minus f zeros, okay? So what this tells you? So it tells you if you have functions f prime t, okay, you apply a Laplace transforms, so it will be transformed into S domains where you get S Laplace transforms of f t minus f zeros, okay? So if you apply Laplace transform of ft, you will have big capital F s minus f 0. Okay, so you can find this in Laplace tables. Okay, so finally we jump to example 4. So inside the example 4, we need to find the Laplace transform of f double prime t. So based on the definitions, we have 0 to infinity, exponent negative st ft dt. So equal to 0 to infinity, exponent negative st f prime t dt. Okay, so from example 3, we know that the Laplace transforms of f prime t is equal to s Laplace transforms f t minus f0. Therefore, okay, so if we find the Laplace transform of f prime t, f double prime t, it will be equal to s Laplace transforms, okay, so f prime t minus f prime 0. Okay, so we have s as Laplace transforms ft minus f0. And finally, we have s square Laplace transforms ft minus f minus s f0 minus f prime 0. Okay? Okay, so what have you learned from example 1 until example 4? So the example 1 until example 4, okay, so the transformations from time domain to frequency domains, you can find it in the Laplace transforms. Okay, so how we get from left-hand side in the Laplace transform into the right-hand side, which is referred to frequency domains in the Laplace transform, is by applying the Laplace definitions, okay? So if you apply the Laplace definitions, you can transform a time domain into a frequency domains. So such as what we have done in example 1, 2, 3, and 4. Okay, so you can, for instance, like example 3, okay, so if we have f prime t, okay, we apply Laplace transforms, so we can see in our Laplace tables f prime t, okay, so which is this one, f prime t. So if we have f prime t, we apply Laplace transforms, okay, so we will get s fs minus f0, the same as s Laplace transform ft minus f0. Okay, so this is exactly what we have done in example 3, where you have that equations. Okay. All right, so next sections, we are going to use Laplace transforms to solve differential equation problems. So in example 1, we need to solve these problems. And we have initial value informations. Okay, so the first steps, you need to apply Laplace transforms towards these problems. Okay, so the Laplace transforms symbol is given by that. Okay, so this is a symbol for transformations using Laplace. So if we apply transformations on the differential equation we have, okay, We apply transformations on the y double prime plus 5 is a constant you can bring outside. Apply transformations on y prime plus 6, bring it outside. Apply Laplace transforms for y. And then on the right hand side, we need to apply Laplace transforms 0. Okay, so next, if you apply Laplace transform of y double primes, okay, we have covered this in the previous sections, but you can refer to your Laplace tables. Okay, so on your right hand side is the S domain, and on your left hand side is time domain. So just now we have f double prime. Okay, so we can f double primes is similar as this part where k is equal to 2. So if we apply Laplace transforms of f double primes, it will be similar to this on the right hand side, where we have s square. Okay, since we are using, we are using y just now. Okay, so since we are using y, so we have a big capital Y s minus s small capital Y 0. Okay, so that one's 2 minus 2 will give you 0. Okay, so this whole thing becomes 0. So 2 minus 1 will give you df over dt, which is equal to f prime 0. Okay, so you can use that to replace in the transformations. So that y double prime transformations will give you s square ys minus s y0 minus y prime 0 plus 5. Okay, so find out what is the transformations of y prime. Okay, so y primes is given by this part. Okay, so if you have y primes, you apply Laplace transforms. In the S domains, you get S big capital Ys minus small y0. So use that information to replace in the questions. You get S big capital Ys minus y0 plus 6. If you transforms y, you get big capital Ys. And if you transforms 0, you will get 0 back. Okay, so next you group, you can expand this. Okay, so if you expand, you have 5s ys minus 5y0 plus 6ys equal to 0 with these terms. Okay, so next we can group components that similar. Okay, ys plus 5s ys plus 6ys. Okay, so what else? Minus s y0 minus 5y0 minus y prime 0. Okay, so that part you can combine to becomes ys s squared plus 5s plus 6 minus this part you can put the initial value informations. So s0 give you 2, 5, 2, and y prime 0 will give you 3. Okay, then you solve for ys. So ys will be equal Okay, so that part you bring it to the right hand side. So from negative to become positive as 2s, and this part, if you add them, become negative 13, you move to the other side, become positive 13. And that part, if you bring to the other side, it becomes divide plus 6. Okay, so you have functions ys. Okay, so inside the denominator, you can separate into two parts. Okay, so s, and 2 and 3. Okay, so that give you positive, and that also give you positive. So you have 2s plus 13. Okay, so once you got these forms, the next stage is we need to apply Laplace, we need to apply partial fractions. Okay, so we have 2s plus 13, s plus 2, s plus 3. So if we apply Laplace transforms, we split this into two parts, the denominator. One is s plus 2, and the second part is s plus 3. Okay, so you look at the denominator, the highest power is 1, so you only have a single coefficient. If we take up here a, so the other part will become b. Okay, so you solve it as usual. 2s plus 13, so a multiply s plus 3 plus b s plus 2. Okay, your expense as plus 3a plus bs plus 2b equal to 2s plus 13. Okay, so s and s you can combine, a plus b, s, and 3a plus 2b you can combine as well, equal to 2s plus 13. Okay, so from these two parts, you can come up with two equations. So the first equations, you compare that part with this part. So you have a plus b equal to 2. So that's the first equation. The second equation, you compare 13 and this part. So you have 3a plus 2b equal to 13. So that's the second equation. If you solve 1 and 2, so a will give you 9 and b will give you negative 7. And then you put it back inside your function ys, replace the coefficients a and b, so you have 9 divided by s plus 2 minus 7 divided by s plus 3. Okay, so this ys is come from this part. Okay, so this is in terms of S domain. Since your question is in terms of time domain, so you need to convert back this into time domain functions. Okay, so to convert into time domain functions, we apply inverse Laplace. Okay, so that part we need to apply inverse Laplace of function ys. Okay, so we apply inverse Laplace for 9 over s plus 2 minus 7 over s plus 3. Okay, so if you apply inverse Laplace of ys, it gives you yt, small capital Yt. And 9 is a constant, so you can put it outside. So your inverse Laplace of 1 over s plus 2 Minus 7 is also constant. You can put it outside. You inverse Laplace 1 over s plus 3. Okay, so how to find this? You need to refer to the Laplace table. Okay, so when you transform inverse Laplace, okay, so the way you look at the table is you look at from your right hand side to your left hand side. Okay, so that is how you look if you apply inverse Laplace transformations. Okay, so we try to find it our function just now, okay, which is you have 1 over s plus 2, isn't it? Okay, so that form is similar to this one, where our a is equal to -2. So when we transforms into time domains, it will be equal to exponents -2 for our a t. Okay, so you use that, replace back inside the questions. So we have 9 exponents -2t minus 7. Okay, so this is also have the same form with different a, where you have exponents 3t. So that would be your final solutions. Okay, so what have you done here? You have questions in terms of differential equations where it is in a time domain. So you need to apply Laplace transforms to convert or to transform the questions to a S domain. So once you done that, you apply the partial fractions, find the coefficients, and then solve it. So put it back, and in the final stage, you apply inverse Laplace to convert back into time domain. Okay, so we move to example 2. Okay, so inside these examples, I already have these Laplace tables. Okay, I take it from the Laplace table, so we don't need to refer inside the Laplace table, we just refer here. All right. So we have questions given by that part, and we have initial value information given by that part. So the first steps, we apply Laplace transforms. Okay, so let's say we apply Laplace transforms of y double primes minus 2 Laplace transforms of y primes plus Laplace transforms of y equal to, we apply Laplace transforms of 3 exponent t. Okay, so these ones will give you that part s squared ys minus sy0 minus y prime 0 minus 2, and y prime t transform give you that as ys minus y0 plus, and yt transform will give you that part which is ys. And this whole thing will be equal to, we take Laplace transform of these things, okay? So 3 is a constant, you can bring it outside, okay? So exponents t is similar to that part where a is -1. So you have 1 over s minus 1. Okay, so next we try to solve it. We have s2ys minus sy0 minus y prime 0 minus 2s big capital Ys plus 2y0 plus ys equal to 3 over s minus 1. Okay, so we group ys with ys. We have s2 ys minus 2s ys plus ys minus sy0 plus 2y0 minus y prime 0 equal to 3 over s minus 1. Okay, so we combine the part. You have ys s squared minus 2s plus 1 minus s. So you can put the information given by this, okay? So y0 will be equal to 1 plus 2, 1 minus, and y prime 0 equal to 1 also. Okay, so we solve for ys. So these ones will give you, okay, so plus 2 minus 1, we got plus 1, isn't it? So we have minus s plus 1, 3s minus 1. Okay, so that part, we can bring it to the other side. So it becomes positive s minus 1. Okay, so that one no longer exists. So we have ys s squared minus 2s plus 1 equal to 3 plus, okay, so that part we need to make it equals the denominator, so we multiply with s minus 1. Okay, so it will give us 3 plus s squared minus s minus s plus 1, s minus 1, this plus 1. Okay, so overall it gives you s squared minus 2s plus 4 s minus 1, which is equal to ys s squared minus 2s plus 1. Okay, so we solve for ys. So that part we bring to the right hand side. Okay, so we have that functions ys. So what next? Can we separate this part denominator? Okay, so that part we can write as well as, okay, so we can write, so s squared will give us s, 1 will give us 1, 1, and negative 2s will give us negative 1, negative 1. Okay, so it becomes s squared minus 2s plus 4 s minus 1 to the power of 3. Next, we apply Laplace transforms for our functions ys. Okay, so let this do it up here. So apply Laplace transform, apply partial fractions on ys. Okay, so what is our ys just now is equal to s squared. Okay, so it's equal to s squared minus 2s plus 4 divide s minus 1 to the power of 3. Okay, so for this denominator, okay, the way we split it or separate it, it will becomes with first part s minus 1 to the power of 1 plus s minus 2, plus s minus 1 to the power of 2, and the third part s minus 1 to the power of 3. Okay, so we can decompose s minus 1 to the power of 3 to become these three parts. Okay, so you can refer this in the partial fractions tables. So the highest power in here is 1, so we only have one single coefficient where we have a and b and c. Okay, so this one also highest power is 1, highest power is 1. Then we solve it these equations. We have x squared minus 2s plus 4 equal to, okay, so a will be multiplied with s minus 1 to the power of 2. We want to make it to the power of 3. Plus b, s minus 1 plus c. Okay, so if you solve this part, okay, so if you solve this part, you will get a s squared minus 2as plus bs plus a minus b plus c equal to s squared minus 2s plus 4. Okay, so how many equations we can get from here? The first ones we have a, okay, so a equal to 1, so that part equal to that part. So that's the first equation. So our second equation is this part and that part, which is negative 2a plus b equal to negative 2. That's the second equation. And then the third equation, a minus b plus c equal to 4. Okay, so if you solve these three equations, you will get a equal to 1, b equal to 0, and c equal to 3. Therefore, your functions ys, okay, therefore, your function ys will be equal to a is 1, s minus 1, plus you don't have b, so it becomes 0. C is 3, divide s minus 1 to the power of 3. Okay, so that is your ys functions after you put the values of the coefficients a, b, and c. So next we convert into time domains, then we apply inverse Laplace. So we apply inverse Laplace of ys, and then inverse Laplace of 1 over s minus 1 plus 3 is a constant. Okay, so you can bring it outside. We take inverse Laplace of 1 over s minus 1 to the power of 3. Okay, so that ones will give you yt equal to, so that part give you exponent t plus, okay, 3 over 2 t square exponent t. Okay, so you can find out in the Laplace table to find the inverse transformations. Okay, so now we move to example 3. So this is the equations that we need to solve given the initial value informations. Okay, so this is the transformations tables, and that one should be positive 4. Okay, so the first steps, we apply Laplace transforms on y double primes plus Laplace transforms on y equal to Laplace transforms on sine 2t. Okay, so y double primes will give us s square big capital YS minus SY0 minus Y prime 0 plus, so that one gives us YS equal to 2 divided by S squared plus 4. So we group YS with YS. So YS x squared plus 1 minus S Y0 will give you 2 minus Y prime 0 will give you 1. Okay, then we solve for YS. We have YS S squared plus 1 equal to 2S squared plus 4 plus, okay, we move to the other side, 2S plus 1. And we further solve for YS. So give us 2 S squared plus 4 S squared plus 1 plus 2S S squared plus 1 plus 1 S squared plus 1. Okay, so next we apply partial fractions. Okay, but before that, if you look at this part, okay, and that part, so these two parts we actually can apply direct transformations, Laplace transformations. Okay, so because of that, we don't need to apply partial fraction for this part. Okay, so we only apply partial fraction for that part. So we have 2 divided with s squared plus 4 s squared plus 1. Okay, so the denominator parts, we can split it into two parts. Okay, we can split it into two parts to become s squared plus 4 and s squared plus 1. Okay, so for the coefficients on top of the denominator, remember you have the highest power if is 2 inside the denominator, so which means your coefficient on top of it must have s. Okay, so in that case we have as plus b. You can refer this in partial fractions tables. And for the second terms, okay, we have cs plus d. Okay, so now you can solve it. Okay, so you need to make the denominator equals. So we take as plus b, we multiply with s squared plus 1. Plus, we take cs plus d, we multiply with s squared plus 4. So the whole equations will be equal to 2. So further, you can expand these equations, okay, to becomes a s to the power of 3 plus as plus bs squared plus b plus cs to the power of 3 plus 4cs plus ds squared plus 4d. So it's all equal to 2. And then you group s to the power of 3 with a plus c s to the power of 3, and then you group s squared plus b plus d s squared plus a plus 4cs plus b plus 4d equal to 2. Okay, so how many equations can you get from these equations? You have 4 unknown variables, so you should have 4 equations to solve. Okay, so the first ones we have a plus c equal to 0 for the S3. Okay, so that our first equations. Our second equation is for the S square. So we have b plus d equal to 0. Our third equation is for S. We have a plus 4c equal to 0. And finally, our fourth equations, b plus 4d equal to 2. So that would be our fourth equation. So if you solve these 4 equations, it will give you a equal to 0, b equal to negative 2 over 3, c equal to 0, and d equal to 2 over 3. So once you got your a, b, c, and d, you put it back the informations inside the equations. Okay, so these ones will give you, so your a is 0, so your b will be equal to negative 2 over 3 s to the power of 2 plus 4 plus c is 0, so d is 2 over 3 divide s squared plus 1. Okay, so with that informations, you put it back. Okay, with that informations, you combine back inside your ys. Okay, so the ys will give you the functions ys will give you negative 2 over 3 s squared plus 4 plus 2 over 3 s squared plus 1 plus 2s s squared plus 1 plus 1 s squared plus 1. Okay, so if you apply Laplace transforms, okay, so apply inverse Laplace transforms on ys. Okay, so these ones will give you, you can do like this. Okay, so I just write down the solutions. Okay, so you apply Laplace transform 2 over s squared plus 4. Okay, so that's the first part. The second part, 2 over 3, Laplace transforms 1 over s squared plus 1 plus 2, Laplace transforms s squared plus 1 plus Laplace transforms 1 s squared plus 1. Okay, so what I did here is, okay, I tried to simplify. I put out some of these constants outside, so I just apply Laplace transform inside the bracket. Okay, so in order to do this, you must refer the Laplace tables because you want to match, you want to find which forms that you can use when you want to apply inverse Laplace. Okay, it should be inverse Laplace. Okay, so finally your yt will be equal to negative 1 over 3 sine 2t plus 5 over 3 sine t plus 2 cos t. Okay, so finally you will have these solutions. Okay, so I have simplified these solutions to get these expressions. So next is example 4. Using Laplace transform to solve these problems with the given initial value informations. And this is taken from Laplace tables. Okay, so the first steps, we apply Laplace transforms on y double prime plus 6 Laplace transforms on y prime plus 9 Laplace transforms on y, and then Laplace transforms on 0. So it gives you s square ys minus sy0 minus y prime 0 plus 6. Okay, so that one gives you s ys minus y0 0 plus 9ys equal to 0. Okay, so you can further put ys with ys plus 6sys plus 9ys minus sy0 minus 6y0 minus y prime 0 equal to 0. Okay, so ys combined become s2 plus 6s plus 9 minus s. So what is your y0? Your y0 is negative 1 minus 6. y0 is negative 1 minus y prime 0 is 6 equal to 0. Okay, so that one gives you positive s, positive 6 minus 6 equal to 0. So ys s squared plus 6s plus 9, and that part you can cancel. So finally you solve for ys, will give you negative s divided with s squared plus 6s plus 9. Okay, so you can further separate the denominator to become s 3 plus plus. So you have negative s plus 3 squared. Okay, so next apply partial fractions. Okay, so we have negative s plus 3 square. Okay, so this part we can separate the denominator part, we can separate to s plus 3 to the power of 1, and the second term s plus 3 to the power of 2. Okay, so the coefficient will be a and b. And then we solve it. as plus 3 plus b equal to negative s. Okay, so how many equations we have here? So that one's as plus 3a plus b negative s. Okay, so the first equations you got a equal to negative 1. Okay, the second equations you got 3a plus b equal to 0. So that's your second equations. Okay, so if you solve these two, your a is negative 1 and your b is 3. So you put it back here. Okay, you put it back here. You got your ys equal to negative 1 over s plus 3 plus b is 3 s plus 3 squared. Okay, so we apply inverse Laplace for ys, and then inverse Laplace, The negative part, you can bring it outside. So we only apply 1 over s plus 3. Plus 3 is a constant you can bring outside, so we apply inverse Laplace s plus 3 squared. Okay, so that will give you yt equal to negative exponents negative 3t plus 3t exponents negative 3t. Okay, so you can refer to the inverse Laplace tables. Okay, so the final solution is given by this one.